Um, in this video, I'm going to talk about the unitary matrix. Okay, so what is a unitary matrix and why do we have to know anything about it? What and why? Um, okay, so I believe most of the students in this class are familiar with the basics of quantum mechanics. You have taken a course or two on quantum mechanics before you showed up for this class. And so you probably know a lot about wave functions and how to solve for them, what are the eigenstates of a given Schrodinger equation and so on. And we're trying to use quantum mechanics to learn about quantum information sciences. And my view is that the quantum mechanics for a quantum information emphasize or must emphasize two aspects, which are normally not that heavily emphasized in ordinary quantum mechanics courses. And one of them is the notion of state. Okay, which is formally written in this fashion. Rather, most of the language used in the quantum courses is the wave function language. And of course, they are the same thing. But because we use the word wave function so much, we tend to forget that actually the more fundamental object in quantum mechanics is a state. It's not the wave function, but it's the state. And wave function turns out is just a way of expressing the content of that state using the explicit coordinate dependence of that state in order to write down the state in the form of some function. The function being a function of space-time coordinates. Okay, so although the notion of a state is perhaps more abstract than that of the wave function, it's still the case that the more fundamental concept in quantum mechanics is a state. And I believe it's quite important that one feels comfortable around these notion of a state and also be able to play around using the state formalism without having to convert it to the wave function formalism all the time. Okay, and so the second aspect that deserves much more emphasis in the quantum information course, I believe, is the notion of a unitary matrix. And in fact, when I was an undergraduate student and studied my own quantum mechanics, I don't believe I ever heard about unitary matrix at all. And it's perhaps only a few years later in graduate quantum course that I first had my exposure to the unitary matrix and what to do about it. But still, even then, I think my understanding of what this unitary matrix really does for us was not really more than a vague concept. Okay, so I don't want my students, to repeat the same mistake that I have made as a student. So I will try to give you an early and pedagogical exposure to what the unitary matrix is and how to write them down and what good it serves for us in handling the theory of quantum information and also the theory of a two-level quantum mechanics. Okay, so let me start with a simple example. Simple example, of course, being the example derived from the two-level quantum mechanics. So I think I emphasized at the beginning of this course that pretty much everything you ever need to know about quantum mechanics is already contained in the quantum physics of a two-level system. And here is yet another instance of that statement, namely that pretty much everything you ever need to know about unitary matrices is already in the formalism for treating two-level quantum mechanics. Okay, so previously I introduced these two eigenstates. Also known as the coherent states, which are mutually orthogonal and normalized to unity, of course. Sorry, this is that. And I said that this two states diagonalize my Hamiltonian with both a +1 eigenvalue and -1 eigenvalue. Okay, so that was that. And now I'm going to do something more interesting with these two eigenvectors. So of course, this is a vector and this is a vector. And if you combine these two vectors together into a bigger object, then you end up with some matrix. Okay, so I'm gonna copy the content of my first eigenvector into the first column of my big matrix, like that. And I'm gonna copy the content of the second eigenvector into the second column of my big matrix. Okay, so all I did is just simply collect the two eigenvectors into a single 2x2 matrix. And I'm going to call that U. And I'm going to make a claim that this matrix is unitary. Sorry, U. Yeah. So the property of a unitary matrix is that if you take the Hermitian conjugate of that matrix, then it automatically becomes the inverse matrix. Okay, so for a unitary matrix, finding an inverse, it's basically trivial. All you have to do is take the transpose and complex conjugate all the elements. Okay. So first of all, we owe it to you. I owe it to you to prove that this is really a unitary matrix. And well, you can just do it. Okay. So what do I mean by just doing it? Well, I just write down the matrix elements for the U dagger, which is putting the column elements into a row element, not forgetting to take its complex conjugate, of course. So then U dagger would be this thing. Okay, and then you just multiply that thing with the U matrix we wrote down in the previous slide here, and you just do some simple multiplication, and and surprisingly, you end up with a unit matrix. Well, if you want to be really certain, then you can also do this matrix multiplication, which will also show you the same unitary matrix as a result. Okay, so this is nothing but the definition of a unitary matrix, and that's nicely that property is nicely being obeyed by simply putting together the two eigenvectors we have derived previously. Now, here's an even more interesting fact. Once you have this unitary matrix at your disposal, you can also prove that if you multiply the Hermitian conjugate of the unitary matrix to the left of the Hamiltonian matrix and the unitary matrix to the right of the Hamiltonian matrix, then this thing becomes diagonal. With the elements being the two eigenvalues we had derived earlier, epsilon plus and epsilon minus. Okay, and this sort of magic happens all the time, always, because in general, if I have n by n Hermitian matrix, so this statement is not even about physics. It's about a fairly well-known theorems in linear algebra. So if you have a n by n Hermitian matrix, then you can write down, you can derive all its eigenstates. Okay, so now maybe this is not a very good notation. I should say alpha, epsilon alpha, and alpha goes from 1 to n. Okay, so in general, for an n by n Hermitian matrix, you can come up with n different eigenvectors that are mutually orthogonal. And with the help of these n different eigenvectors, you can construct a n by n unitary matrix by simply arranging all of these eigenvectors so that the first eigenvector occupies the first column and the second eigenvector occupies the second column, etc., all the way up to the nth eigenvector occupying the final column of the matrix. Okay, now once you have constructed the unitary matrix in this manner, then it's straightforward to define its Hermitian conjugate and show that this will always satisfy the unitarity condition. And furthermore, if you make this sort of a matrix product, flanking the initial Hermitian matrix on either side with U dagger and U, then remarkably the result is a bunch of eigenvalues occupying only the diagonal entry with every other entry being 0. Okay, so there's a big 0 over there, big 0 over there, and it's just these diagonal elements which are being non-zero and represent none other than the eigenvalues of these Hermitian matrix. Okay, so this is a very simple and beautiful and extremely powerful result one can get from pure mathematics. And the amazing thing is that this purely mathematical result has a direct direct implication in the way we describe the physical world, the quantum world, nonetheless. Okay, so I have made a bunch of really fantastic statements without ever offering any sort of proof, and so that's not very fair. So now let's go into some proof. Okay. So first, I will make a proof in the case of a two-level system, and I'm going to formally write down my my two column vectors as simply 1 and 2. So this is a slight difference from the previous expression where I use n for here and minus n for the second column vector. But hopefully you will forgive me for this change of expression. Now, the conjugate is actually, you can write these conjugate Hermitian conjugate matrix like this. Okay, so remember that if a certain wave vector, a certain eigenvector has this sort of pair of complex numbers, that means this is a procedure by which you convert the column vector into a row vector. So first of all, you make this column to row conversion, and secondly, you complex conjugate each element in that row vector like that. Okay, so by doing so, you can precisely define the elements, all the elements in this first row vector, and you can also precisely define all the elements in this second row vector simply by converting this column into a row and not forgetting to take the complex conjugation of all its elements. Okay, so that's a way to go from a unitary matrix construction to the construction of its Hermitian conjugate. Okay, so now actually using this formulation, it's quite easy to prove this statement. No, this is the wrong order. Sorry. Okay, so U dagger has this form. So 1, 2, and U has this form. So 1 and 2, like that. And now we do a multiplication of these two matrices as if each of these state vectors are just numbers. Okay? And if all of these were just numbers, then the result of the matrix multiplication will be like that. Okay? And believe it or not, this is exactly the result you will get from an explicit calculation of the matrix product U dagger U. Okay, so well, if you have doubts, then you can just write things all out in terms of components and convince yourself that this is indeed what you get. Now, well, this is by normalization equal to 1, and this is equal to 0 by orthogonality, this is equal to 0 by orthogonality, and this is equal to 1 by normalization. So thankfully, we really seem to have a unitary matrix. And we have proven it in this very simple manner. All right, so let's see if I can prove the other piece of fantastic statement, namely that U dagger HU will diagonalize the Hermitian matrix into a diagonal form. Okay, so I'm going to use the same formalism, so which expresses the U dagger like this. So I'm going to just copy that. 1, 2, and then this is H, and U is 1 and 2 in the column fashion. Okay, so again, I'm going to have H directly act on the first and the second eigenstates, which will give me this. Okay, but both 1 and 2 are the eigenvectors of these Hermitian matrix to begin with, which means I can replace this H1 by epsilon 1 being the eigenvalue, and I can replace this by epsilon 2. Okay, and further completing the calculation by working out the matrix multiplication between these two objects, which kind of look like two. This kind of looks like a row vector, and this kind of looks like a column vector. In fact, both are 2 by 2 matrices, but pretending that each of these is a vector and each of these is some number will give you the correct result just as well. So I'm going to proceed. So the first entry is this. The second entry is this multiplying that. So it's 1 and 2 overlap. And this is epsilon 1, 2, and 1 from the product of this and that. And finally, we have 2 and 2. Okay. And now some of the elements are 0. Oh, sorry, this better be 1, right? Yeah. So right, because 1 overlap with 1 is 1, 1 overlap with 2 is 0, etc. Okay, so indeed, this is the diagonalized version of the Hermitian matrix as promised. And you can see right away that nothing in this process of proof is specific to a two-level system. You can keep adding more column vectors over here. You can keep adding more row vectors over there, etc. And the proof will go through just as well. And the final result will be diagonal matrix with diagonal elements epsilon 1, epsilon 2, epsilon 3, and so on. Okay. Yeah, so there's nothing specific in this way of proof that's limited to a two-level system. It works for any n-level system with n by n Hermitian matrix. And so we have basically a proof. Okay. So here's a summary, because we learned a lot in this a short amount of time. and maybe the information is a bit too much to digest right away. So the summary of what I said is the following. H, of course, being a general n by n Hermitian matrix representing some sort of a physical Hamiltonian for a n-level quantum system, has a bunch of eigenvectors and eigenvalues, and all these eigenvectors are mutually orthogonal, or they can be made to be orthogonal. And once you have found all of these orthogonal eigenvectors, then you can use that to construct the unitary matrix. Alpha equal to 1, alpha equal to 2, and then alpha equal to n. And its conjugate, which is 1, 2, all the way down to n. Okay, and this unitary matrix is guaranteed to have this nice property that after performing this sort of multiplication by U dagger on the left and the multiplication by U on the right, will transform the original Hamiltonian or original Hermitian matrix into its diagonal form. Okay, and by the way, this sort of transformation is called unitary transformation, and both the notion and the expression unitary transformation will show up repeatedly, I think, in the course of this lecture. In fact, you can almost say that most of what the competent quantum computer does is to perform unitary operations or unitary transformations on the quantum states. Okay, so without having a good grasp of what the unitary transformation or the unitary matrix is, you're not properly equipped to understand anything about quantum computation, which is why I want to emphasize both the technique and the notion of a unitary transformation at this stage. Okay,